Good evening, everyone. Thank you for joining us tonight. Welcome to the Avexia webinar series. Our topic for tonight's special webinar is vitamin A the missing piece of the puzzle for microcytic anemia? My name is Joanne Iverson. I am the Director of Client Relations for Avexia Diagnostics and will be your host for this evening. Tonight, I have the distinct pleasure of being joined by an exciting guest, Dr. Bryan Walsh, who will be our presenter for this webinar. Dr. Bryan Walsh has been studying human physiology and nutrition for over 25 years and has been educating others in health for 20 of those years. When he isn't teaching, he spends his time poring over the latest research and synthesizing his findings into practical information for health practitioners to use with their clients. He has lectured to members of the healthcare industry around the world and consistently receives positive feedback in his seminars and courses. His online educational platform, Metabolic Fitness, helps health professionals to stop guessing and start knowing what to do with their patients. While Dr. Walsh is known for his expertise in biochemistry and human physiology and his unparalleled ability to educate on these topics, he is perhaps best known for challenging traditional dogma in health and nutrition concepts, such as questioning current models of adrenal fatigue, glucose regulation, detoxification, mitochondrial dysfunction, and more. As such, he has been sought out to consult with multiple companies, academic institutions, and wellness organizations. Dr. Walsh is also a board-certified naturopathic doctor who has been seeing patients throughout the U.S. for over a decade. Joining Dr. Walsh tonight will be Dr. Wayne Sedano, our Director of Clinical Support and Education at Avexia Diagnostics. Additionally, Dr. Sedano is the Director of Integrative Medicine Education for the College of Integrative Medicine and lectures and teaches internationally. Before we begin, just a bit of housekeeping. We encourage participation. So if you have a question, you may submit your questions in the questions field in the right-hand area of the interface. We will answer submitted questions toward the ends of the presentation. In addition, there is a handout section below the questions where you can download the slide deck to be able to have. If your questions are not answered this evening, you will surely receive an answer by email within a day or two, and we can also send those slides to you as well. Without further delay, I will now turn the webinar over to Dr. Walsh.
Great, thanks. Can you hear me okay? Yes?
Yeah, you sound great.
Okay, great. All right, so thanks for being here. Thanks for having me. I'm probably just going to jump right in. I don't have much of an intro here except to say that our job as practitioners is to try to find the most underlying situation physiologically that's going on with our patients and our clients today. And I think that sometimes we miss things, and that's nobody's fault, but sometimes if there's not enough information that's presented, then maybe we're not doing things as optimally as we can. Maybe it's in lab testing, maybe it's in different kind of supplements. And so there's this concept, I might change this so I can actually draw, of microcytic anemia. So microcytic anemia is small-celled anemia. There's a whole bunch of different types of anemia. I'll just start here. There's a bunch of different types of anemia. I have some slides on this, but I'm just going to go ahead and do the too long didn't read kind of thing. So anemia, really, conventionally, they say it's low red blood cells. And that's doing a huge disservice to a bunch of patients because it's not just low red blood cells, it's really the inability to deliver oxygen to the cells of the body. And of course, all cells have sort of an aerobic nature to them, and they need oxygen in order to function properly. So if you just say low red blood cells, you're missing people because, as you probably know, hemoglobin is the oxygen carrying component within red blood cells. And so somebody can have normal red blood cells, but low hemoglobin, and they will have an inability to functionally or optimally deliver oxygen to all the cells of the body because they lack the oxygen carrying component, which is hemoglobin. So if you lack hemoglobin, you usually end up with small red blood cells because, according to Guyton's physiology textbook, there's 280 million molecules of hemoglobin inside a single red blood cell. So if you don't think the body is amazing, or the creator of the body is amazing, 280 million molecules of hemoglobin inside one single red blood cell is like mind-boggling. So if you don't have enough of that, then the red blood cells will be small. And the nice thing is that when it comes to microcytic anemia due to low hemoglobin, let's just say, many times the cause is nutritional. Not always, but many times. So what I'm saying is if red blood cells are normal, but hemoglobin's a little bit low, that patient might have symptoms of anemia, which we'll cover. And not always, but there's a good chance that they're not making hemoglobin appropriately. And because, as you will see, there's a bunch of different vitamins, minerals that go into the synthesis of hemoglobin, there's a good chance that they're missing that. Now, it depends on how long you've been a practitioner or what you've listened to. The common ones, iron is of course the big one, but there's iron, B6 deficiency can do that, zinc deficiency can do that, copper deficiency can do that. Vitamin C loosely can. Copper and vitamin C both help iron to work better, I'll just say, in terms of making hemoglobin. But vitamin A, and what I'm going to show you throughout this presentation, it's a very interesting story. And it's, first of all, the majority of conventional medicine says that most people in industrialized nations are not vitamin A deficient. That's really a third world country issue. And it very much is a third world country issue, very much. But what I'm going to show you is that it might be more of an issue here than we realize. And testing and assessment of it is not as easy as just running a marker or two. And I'll show you that as well. And then at the very, very, very end of this, I'm going to show you some really compelling studies that even if somebody is iron deficient and or zinc deficient and is showing a microcytic anemia, vitamin A has some profound impacts on hemoglobin, yet despite the fact that it's over 100 years old, the actual reasons for that are still under conjecture. It's a fascinating subject. Anyhow, so let's just go ahead. And feel free to ask questions. There'll be some time at the end to do this. So I'm just going to cover, just for anybody kind of, I want to say like the uninitiated, that doesn't really know about what anemia is. We're just going to briefly, very briefly cover it. It's a fascinating topic. I love anemia. Erythropoiesis, hematopoiesis, all those different things. We're going to look at vitamin A. We're going to talk about, are we deficient in it? If we are, how should we assess people for that based on the scientific literature? Again, none of these opinions are really mine. I try to take what I can from the evidence as much as I possibly can. There's a conversation amongst a lot of people that beta carotene converts into retinol, and it does, but how well does it? And can we rely on that alone to say, well, I'm getting adequate enough of beta carotene in my diet, therefore I'm probably sufficient in the fat-soluble vitamin A, retinol, for example. I do want to look at interactions with other micronutrients. This is a fascinating subject as well. And, it really then begs the question as to why sometimes we're focusing on just one micronutrient and giving people a lot of those particular things because the interactions are very compelling themselves. Then finally, we're going to look at this vitamin A anemia connection, which I have a paper that says it's decades old. This is well known. However, in the functional medicine industry, I can tell you it's not one that's talked about very often. Some people might be, but as a whole, it usually doesn't get talked about in much of the education or even in the functional medicine circles. And then there's just three, and it's proposed mechanisms. Science is still not entirely clear on those. And then I'm going to show you how vitamin A can improve anemia by itself. And if not improve anemia by itself, actually, I'll just say it's kind of supercharge the other things you're doing for a microcytic anemia, like zinc or iron. And then finally, just briefly, kind of what to do, although the what to do is pretty self-evident, I think, as we go through this story. So what is anemia? I just said this. Conventionally, it's most definitions, when you look in conventional medicine, will say the number of red blood cells is lower than normal. Sometimes you'll see they'll mention hemoglobin. It's really rare that they say that, however, and that's a problem because, as I just said, I think functionally is, to me, call it anemia if you want, but what really it is it's an inability to deliver oxygen to the cells of the body. And I have some symptoms just in a second, but the number one symptom, of course, of anemia is fatigue. Why? Because you can't get oxygen to the cells of the body. They're basically gasping for air. They overproduce CO2, which then makes the body slightly more acidic, and fatigue is the number one symptom. A second one is we'll call it exercise intolerance, especially for aerobic activity. Same deal. You don't have adequate amounts of oxygen, so they're kind of gasping for air. They build up a CO2 that slides over, basically increases lactate, changes the pH, and then enzymes don't work as well. So they don't have the tolerance for exercise that they might normally if they were adequately oxygenated. So what I'm suggesting is, call it what you want. It's not low red blood cells, but if the red blood cells are too big, they're too small, they're too few, or they lack the oxygen carrying component, which is hemoglobin, then this person will have symptoms of anemia. Even though they might not get the diagnosis of anemia, You can call it a functional anemia, or really physiologically, the accurate way of suggesting this is you're not adequately getting oxygen to the cells of your body. So the primary signs, the number one, hands down, is going to be fatigue. You might get some weakness, and then I said exercise intolerance, and this is mild. Okay, now there are really significant symptoms of anemia, and I'll show you that it can be problematic. But if it's, and some of you, depending on the demographic that you serve, might see patients like this that have really low red blood cells, really low hemoglobin, and are, frankly, anemic. They can get things like irregular heartbeat, dizziness, chest pain, cold hands and feet. These are the ones that their pallor will change a little bit of the conjunctiva of their eyes, or you can look inside their lips. It can actually change their color because it's pretty significant. But in anybody that has this, and I will tell you, I've seen a lot of patients that had fatigue, but they didn't know why. Their markers were within the reference range, but when you looked closely at it, they were not getting oxygen to their cells properly. So, but not only that, now here's one that's not talked about very often, and this is cognitively. Now this would also make sense, but I'll just tell you, you can look up signs and symptoms of anemia in most medical textbooks, and this is what you'll see. And what you won't see is the other parts, and this makes sense also. If you can't get oxygen to the cells of the body, you're not going to get it to your brain either. And so it turns out cognitive functions are related to hemoglobin. By the way, notice that it doesn't say are related to red blood cells or red blood cell count. It's related to hemoglobin. That's the most important marker in the first three markers or indices of a red blood cell count. It's not red blood cells. It's not hematocrit. Hematocrit is helpful, I suppose, but doesn't really tell you too much. It's hemoglobin. It's how much hemoglobin are they making to carry around oxygen to the body. And so cognitive function was strongly related to hemoglobin, and those with low hemoglobin levels compared to those with higher hemoglobin levels. Here's another paper, same thing. Decreased brain hemoglobin, not surprisingly, can lead to low oxygen levels, one of the most accepted theories of the relationship between anemia and dementia. There's a lot of different theories. It hasn't been proven, but that's one of the most accepted, and it also makes a lot of sense. So if you have patients that are tired, having a difficult time, maintaining exercise, cardiovascular exercise, and they're having, what people usually call senior moments, I think it's a good idea to run the most inexpensive panel you possibly can. That's just a basic CBC with differential. Here's another one. Why should we even be paying attention to anemia in the first place? In serious anemia, that can cause cardiovascular issues. It requires the heart to pump longer. I'm sorry, not longer, harder. And if over time it's contracting harder, it is a muscle, and then you can get cardiovascular issues. But not only that, this was showing, and look at what it says. This is huge. After controlling for many potential confounders, it says mild grade anemia. Mild grade anemia. This is not severely anemic, but was found to be prospectively associated with clinically relevant outcomes such as increased risk of hospitalization and all-cause mortality. We need to be taking a better look at a standard CBC. Again, probably the most inexpensive part on a standard blood chemistry, and taking a real hard look at this using optimal reference ranges and making sure that that's optimized first before jumping to some of the exciting, flashy, sexy, sparkly tests that we're running today. So here's just a real super quick summary. Is if anemia is associated with a number of common symptoms like fatigue, cognitive dysfunction, etc., and if it's associated with chronic conditions, including mortality, cardiovascular issues, and it's occurring at a rate that's not being noticed by labs or doctors because they're not looking at an optimal reference range, which we'll look at in just a second. If there's a number of potential nutritional reasons for it, which I've already mentioned, iron, zinc, B6, copper, vitamin C. What you'll see today is vitamin A, as well as macrocytic anemia, which is looking at things like B12 and folate, of course. Then we should be doing a much better job identifying and determining why it's happening. And once again, I talked a little bit about this in the last webinar that I did. There is no better lab test than a blood chemistry. It's the most established, scientifically proven, validated, internationally recognized, inexpensive for all the things that you get on it, a test that has more science behind each and every marker, including optimal reference ranges, than any other test out there. We need to be doing that test first and foremost, looking at it with optimal reference ranges, looking at the latest science as to why markers might be out of reference range. I'll just give a really quick example, but there was a paper that basically showed a correlation between HDL and leaky gut. And the higher the HDL, the more there was intestinal permeability. So why are we not using HDL levels and sort of a screening test for intestinal permeability in the first place. There's so much literature on all this stuff. We don't need to be doing all the, at least the first line of testing shouldn't be a bunch of functional medicine labs. It needs to be blood chemistry, especially, and this is what I'm saying, a CBC. It's so inexpensive and you can tell so much of what's going on. Anyhow, so there's a couple asterisks on this, and I realize that this almost messes up the flow, but I have to say this. This needs to be stated. And I have like a good dozen of examples of this in the body. And that is, we as people are really good at finding a problem in something and then feeling like we need to fix it. But when it comes to the body, the question becomes, is the body doing this on purpose to protect it? Or is it serving some larger thing that we're not aware of? And we're trying to intervene and fix it and correct it. Low cortisol is a perfect example, not adrenal fatigue, but instead probably suppression because the body's desire for certain aspects of the immune system. But what I'm going to say here is, so I'll actually slow down just a little bit. There's something called anemia of chronic infection. Okay, that could be chronic infection, chronic inflammation, chronic disease. It's all had the same names. They're all basically synonymous. What happens when, in the state of chronic inflammation, chronic infection, chronic disease, typically you have proteins go up. You have cytokines go up, immunoglobulins, IgG antibodies. They'll go up. Now, these are proteins. Now, blood viscosity is a fascinating conversation by itself, but really, next to water, you could argue red blood cells, proteins are the most abundant component in blood. And so if proteins go up, so too will the blood viscosity. Now, blood viscosity means there's more shear forces going along the capillary walls, basically the walls of all the different vasculature. In addition to that, there's a whole bunch of it's associated with it. It might have glucose dysregulation because of this. It's more viscous blood. It has to work. The heart has to work harder. There's more friction and shear going across the vessels. So to compensate for that, the body is like, wow, I need these cytokines. I'm in a state of inflammation. I definitely need these immunoglobulins because I'm fighting off an infection or something, autoimmune disease or whatever. And so, man, this blood is viscous. What can I do to decrease its viscosity? Well, you could add water, make somebody super thirsty, but that's not really going to work. So what it does is it decreases red blood cells because proteins and red blood cells are the strongest contributors to blood viscosity. And so if you have a whole bunch of proteins in there and you have a whole bunch of red blood cells and you need the proteins temporarily for whatever infection or inflammation you have going on, the body's going to purposely decrease red blood cells. And so I want to say that this is an example of maybe we don't need to always intervene. And I just want to show you. So anemia is not always problematic. There's another example. I won't get into that now. It has to do with acidity, but it's not always problematic. Okay, so just remember that. Just as a side note. Okay, I'll get back to the regularly scheduled program here. All right, so hematopoiesis, blood synthesis, heme synthesis, erythropoiesis, red blood cell synthesis. We're going to look at how hemoglobin is made. Okay. So red blood cell indices, the top three, the first three I should say, are red blood cells, hemoglobin, hematocrit. I've made hemoglobin with an asterisk in red because, in my humble opinion, it is the most important of these three markers in determining if somebody has an inability to deliver oxygen to the cells of their body. So these indicate if hemoglobin is low, that indicates an anemic tendency. Most medical doctors have to see red blood cell, hemoglobin, and hematocrit low in order to diagnose with anemia. And again, I disagree. Because if my hemoglobin is low, I'm not going to wait till my red blood cells are also low. And I will also tell you, I can't count how many people I've seen with low hemoglobin only and signs and symptoms of anemia. And then secondly, there's MCV, MCH, and MCHC. I didn't highlight it, but I should have. MCV is the most important of these three, in my humble opinion. It tells you the size of the red blood cell. But the first three indices tell you if there's anemia or not. The second three tell you what type, if it's too big, too small, too pale, too colorful, if you will. And then lastly, what you also see, and I talk about this in great length elsewhere, RDW is one of my favorite markers on a CBC. It's one of the most valuable, I think, especially if you know what you're looking at. It tells you the relative size difference in the red blood cells. If there's a lot of big ones, a lot of small ones, the RDW will be high. If they're all the same size, it'll tend to be lower. But that really helps out quite a bit. It corresponds with inflammation, incidentally. It's a really cool marker. So here is a molecule of hemoglobin. You can see right smack in the middle, there's your iron. It's a polymer, not polymer. That word just went right out of my head. 4 monomers put together. is what it is. Anyhow, so it's the oxygen carrying component of blood. It requires a whole bunch of different things to make it. I'll show you a pretty cool slide in a second. It needs a little bit of, it's not really protein, it's amino acids, vitamin B, zinc, iron, copper, and C, I told you, help make iron work better, but they can show up as a microcytic anemia if you can't make hemoglobin well. And I just threw in, it's also a buffer in blood, which is kind of cool too. All right, so I want to, since we're talking pretty much only about hemoglobin right now, I want to look at a better range, because reference range on a lab is the most important part of that lab, I will tell you, because the markers are important, but there's nothing that's more important than the range. The range dictates whether something is high or low or normal, which then dictates whether you intervene on it or not. And if the range is wrong, well, guess what? Our diagnosis is going to be wrong and our intervention is going to be wrong. So the range is more important than anything. And so what I want to do is take a critical look at the typical hemoglobin range, and I've done this for pretty much every standard blood chemistry marker. But when you look at this particular paper, to kind of orient you to this was done internationally, so it's a little bit different here than the markers that we use, or the values in the US, but all you need to do is add a decimal point. So here you can see it was all-cause mortality risk for women, here's it for men. You can see that here is their reference, and when you go below that, you can see that there's an increased risk for mortality. And you don't have to go too low in order to make that happen. In fact, what they said was, older women with a hemoglobin concentration of, now look at this really closely, 12 to almost 13, were significantly more likely to die compared with those with a hemoglobin of 13 to 14 after adjusting for multiple potential confounders. They went on to say that low normal. Now, what does this mean? This phrase, low normal, anytime you see this in the literature, means it is within the reference range, but on the low side. I'll say that again. Anytime you see that phrase, low normal, in the literature, it means it's within the normal reference range, but on the low side. Okay, that's a problem, because I will tell you, most practitioners, if they don't have their own range that they're working with in their head, and this goes for functional labs as well, they look at the lab and they let the lab tell them if it's high or low. Okay, and so most doctors, if it's within the reference range, there's no problem. Anyhow, so low normal hemoglobin levels has adverse consequences, has motivated reconsideration of the hemoglobin cutoff points, determining anemia in older adults. There's another paper. Now remember these numbers, okay? We got to pay really close attention to this. They said subclinical anemia. What does that mean? Anemia that's kind of flying under the radar and not being noticed by doctors was defined as hemoglobin levels values of 13 to 3.9 for men and 12 to 12.9 for women. That's the exact same thing we just saw in that other darn paper. So based on that, when you look at the traditional reference range of hemoglobin for women is about 12 to 16. Well, if we're waiting until it gets down to 12, you just saw two papers and there's more, that suggests that that's way too low. And therefore, here's what I consider to be an optimal reference range based on the scientific literature. It's not a story that somebody's been telling about what the hemoglobin should be. When you look at those two papers, when you start creeping down below 13, it's a problem, as like I said, evidenced by a couple of papers. So we need to be using a better reference range. Let's take a look at hemoglobin. So in order to make heme, the globin port is protein, that's fairly easy. To make this heme, which is this very last thing down here, is at the very beginning, you can see you need glycine. Now, I'm not going to get into a big conversation about glycine, but it's a super interesting amino acid. I don't want to say that a lot of people are deficient in it. Glycine is one of the reasons why collagen is so darn popular, because a third of the amino acids in collagen are glycine. It's an inhibitory neurotransmitter. Of course, it's used along with taurine to conjugate bile, from bile acids to bile salts. It's incredibly important as an amino acid. I would suggest that some people might be a little bit low in it, because when you give it to them, they can seem to improve. Although you have to be pretty low in glycine to cause heme issues. So you make glycine, and this is fairly complicated, but really what you need to know is, at this particular step, it's a B6 dependent step. Now that means if you have glycine, but you're lacking B6, that you cannot continue this pathway towards heme if you're lacking B6. The next step happens to be a zinc-dependent enzyme. So same thing, if somebody's low in zinc, you cannot make heme adequately. You can't make heme, you can't make hemoglobin. If that weren't enough, of course, you need iron to pop on at the end. And I mentioned before that both copper and vitamin C, in a roundabout sort of way, make iron more usable for heme synthesis. I'll just put it that way. If you lack copper, I'll just make this. If you lack copper, you can't convert iron adequately in order for transport to make it to the bone marrow to be incorporated into heme. So a copper deficiency shows up as an iron deficiency anemia. In fact, it looks exactly like an iron deficiency anemia, but it will not improve until copper improves. So what's this vitamin A connection then? The first thing we need to talk about if we're going to talk about a vitamin A story is who's deficient in the first place. Now, if you just listen to the government, and NHANES data, we'll just say that, they say less than 1% of the US population has serum retinol levels less than 20 micrograms per deciliter, which indicates that the vitamin A deficiency is uncommon in the US population. Okay, so if you just cherry pick papers or you just look at something like this, you say, okay, cool, people aren't deficient in vitamin A. Done. Don't need to think about it. Okay, but as with anything, I think we need to question most things, including me. Feel free. That's why I show you the studies. Is to question things and take a deeper look. So if you do, here's a paper that talked about when the intake of vitamin A is inadequate to meet the body's needs, the liver stores are depleted to maintain serum retinol at normal concentration. So this by itself, and we're not done, indicates that, and the next paper I think shows that serum retinol levels are maintained homeostatically, meaning it tries to keep it at a certain level, which makes sense for deliverability to the cells of the body that need vitamin A. And your liver serves as a storage form of that in order to be able to, if somebody might have temporarily low vitamin A intake, in order to serve the body's needs and maintain retinol at normal. However, if somebody could look at this and say, well, wait a minute, if serum retinol is normal until liver stores are depleted, I don't want my liver stores to be depleted. So if I was to take my serum retinol level, that's not an indication that your liver stores are okay. It's not. It's basically, it's kind of like if your gas tank indicator is not working and looks like it's fine, but in fact your gas level is low. You don't want to run out of gas. So here's another one. In healthy individuals, serum retinol concentrations are homeostatically controlled and do not begin to decline until liver reserves. And here it says is dangerously low. So basically, serum retinol levels will maintain its normalcy until vitamin A levels in the liver become dangerously low. And I think we can agree that that's probably too late at that point. You want to try to catch this beforehand, especially if we're focusing on preventative medicine and optimal health. If you're familiar with vitamin A testing, there's some really interesting ratios about using retinol binding protein, which is a protein made in the liver. It does what it says. It's supposed to bind onto vitamin A and transport it around the body because it is a fat-soluble molecule. The blood's water-based. Serum retinol and retinol binding protein will decrease during times of infection because it's a negative acute phase reactant, which means somebody might look like they're vitamin A deficient when in fact maybe they're not, depending on if they have inflammation. So this is probably my favorite thing here. Because I think about this kind of stuff a lot. It says that although vitamin A was discovered over 100 years ago, they said vitamin A status assessment is not trivial. Now, I really spent a lot of time in this particular area. If vitamin A is over 100 years old and we still don't have a handle on it, how do we even have a sense of the microbiome or genetic testing, epigenetic, nutritional genomics, stuff that people are really interested in? I bring up the point too. For example, I think I used this in the last presentation, but the pentose phosphate pathway is also over 100 years old. It's a second discovered biochemical pathway after glycolysis. Really well studied. It happens in every cell of the body, including red blood cells. And then it was less than about 5 years ago, researchers realized that human beings synthesize erythritol via the pentose phosphate pathway. But yet we've been studying this really, really basic pathway, like even in red blood cells, for over 100 years. And we're like, oh wait, it makes erythritol also. So I'm just saying, we think we know a lot about a lot, and I would submit that I don't think we know as much as we think we do about a lot of things if we don't even have a handle on some of these basic micronutrients that have been around for kind of a while and we've been studying since then. So there's a bunch of papers that have been looking at this, basically, how do we best assess it? This last paper says it. And there's all these papers that are saying, well, how do we evaluate this? Do we look at liver levels or do we look at something else? So here is an example. So if assessment's not perfect and you want to look at what people are eating, because remember, go back to that original paper. It said that most people are not deficient because less than 1% of the population has serum retinol levels less than 20 micrograms per deciliter. All right, so here was a paper, and it was looking at the estimated average requirement. And if you look at over here on the left-hand side, the naturally occurring, so this is just diet. This is saying that 74% of the people were not even meeting the vitamin A estimated average requirement just through food. Less people, I shouldn't say less, more people were getting their vitamin A requirements if they were eating enriched and fortified foods, and even more people were getting it if they were using dietary supplements. But just left to their own devices, most people weren't even getting enough, not even close. And they said even when accounting for vitamin A from fortified foods, over half of adults are not reaching the EAR for vitamin A. Here's another one that was looking at adolescents that says that more than 1/3, not surprisingly when you look at what people are eating today, of adolescents were consuming less than 75% of the vitamin A for RDA. So the question is, who's deficient? And I am of the opinion, I'm stating my opinion, that there's probably more people that are not adequately consuming vitamin A in an optimal level than we necessarily think. So, but that's okay because we have beta carotene to convert, right? So let's take a look at that story. This is kind of an eye opener. So this paper was talking about, okay, I'll put it this way. So what it's called is vitamin A equivalency. And usually this is done in a ratio. And so what it will be is, and I'm just going to kind of make it up here, but let's say it's 20-1. What that basically means is 20 units of beta carotene will convert to 1 unit of retinol. So when you see these ratios, that's really what they're getting at. And they call it the vitamin A equivalency of beta carotene. So what this paper of many are saying is that that equivalency is highly variable. And what I'm about to show you is all the different variables that they identified. So how much beta carotene converts into retinol is controlled by food and diet related factors, including the food matrix, food processing techniques, the size of the dose of beta carotene, and the amounts of dietary fat, fiber, vitamin A, as well as other carotenoids of diet, as well as by characteristics of the target population, such as vitamin A status, nutrient deficiencies, gut integrity, and genetic polymorphisms associated with beta carotene metabolism. And that's just a few. They go on to say the absorption from beta carotene, now follow this, from plant sources ranges from 5 to 65% in humans, which is quite a bit. And vitamin A equivalency ratio, again, here's this ratio, for beta carotene to vitamin A from plant sources can range from 3.8 to 1, which is good, right? So that's 3.8 units of beta carotene converts to 1. That's a great conversion. But it can go up to 28 to 1 by weight, but we're not done. The vitamin A equivalency of beta carotene is likely to be context specific and dependent on specific food and diet related factors in the health, nutritional, and genetic characteristics of human populations, but there's more. So this is actually a really good paper here. They said recent studies report, and if you look at, here's that same ratio, conversion efficiency of dietary beta carotene in the range of 10 to 21 by weight. These data indicated that the bioconversion of beta carotene to vitamin A was, and here's what they say, not as efficient as expected. But wait a minute, I thought we've been studying this for about 100 years. However, this new conversion ratio must be regarded as temporary, basically because there may be more data that comes out in the future. So the question becomes, how well does beta carotene convert to vitamin A? Here's another one. Recent studies reported that the conversion efficiency of dietary beta carotene in the range of 10 to 21, that says the same thing. That was supposed to be a different slide. I'm not sure how that happened. Oh, okay, but listen, so here, forget this. So check out this paper. And this paper looked at, I'm not sure how that happened. So they used trackable beta carotene in this study. It was a fairly small study done, I forget, it was like 11 people. Yeah, 11 men. They gave them this, and their conclusion, if you look at it here, the vitamin A activity of beta carotene, even when measured under controlled conditions using tracer beta carotene, can be surprisingly low and variable. So the point on that one goes back to here, that we thought it used to be something, now we think that it's less efficient, even under controlled conditions. It's surprisingly low and variable, and forget that because that was the wrong one. And then when you toss in underlying conditions, it's questionable how much beta. Here's the question, and you know, I think everybody listening should say, well, how well are my patients beta carotene converting to vitamin? Can I rely on that? Can I trust that? Because, for example, in hypothyroidism, the conversion of beta carotene to retinol is inhibited. I can tell you in type 1 diabetes, it is inhibited. And it's questionable whether it's insulin related or not. You don't typically see that in type 2 diabetes, but so if somebody has some kind of underlying condition, chronic condition, then it's questionable as well. So this big question is how, and remember, this is a big story here. How deficient might we be in vitamin A? Well, when you look at the recommended daily allowance for vitamin A, it's a little higher in men than it is in women, but let's just say it's roughly around 2,500 IUs a day, plus or minus. But then you look at dietary sources. Now, this is preformed vitamin A. This is in retinol form, not in beta carotene. Liver is really popular today, which is pretty cool. I think we might be overdoing it. You got to watch out for copper issues if you're eating a whole bunch of liver, but liver is pretty awesome. I'm not really going to talk about it too much, but yeah, if you're eating liver, then you probably get adequate amounts of vitamin A. But then you start to look at the rest of food groups, and it decreases precipitously. Okay, you kind of have to try hard in order to get these levels of vitamin A from preformed vitamin A from dietary sources. Okay, so the question then becomes is how deficient are people? And basically what I say is assessment for vitamin A status is of questionable utility. I think we've taken a good look at that. It appears that some people are not consuming optimal amounts of vitamin A, and there's a whole bunch of influences that impact the bioconversion of beta carotene to retinol. And so I will state that I tried to show you the evidence, although I'm stating this as my opinion. Our patient's vitamin A status should be considered questionable until proven otherwise. And it's up to us to take a look at it. And the next slide, however, in this world where we don't like to think, and if you don't believe that, oh my gosh, the number of people that are using ChatGTP in order to just answer questions for themselves that they would have tried to find the answers for before, just done a good old-fashioned Google search, or I don't know, looked up in an encyclopedia. But look at this. So this is a cool paper. This was done on Chinese children, so you can take that into consideration. But what they found is that look at this really closely. Dietary vitamin A intakes were significantly correlated with vitamin A stores in the body and liver, but not with serum retinol levels. So what does this mean here? This means using something like chronometer. Track, and I think this paper did it for 2 weeks, track their dietary intake. How much vitamin A, how much of the carotenoids and beta carotene is somebody eating? Do we need to be doing an assessment on this, or can we use our brain? And nowadays, tracking food is easier than ever. My gosh, everything has a darn barcode on it. All you got to do is scan it into your phone and use MyFitnessPal or Chronometer or any of these apps nowadays. It is easier than ever to track somebody's diet, what they're actually eating. So here, this paper said, look at this. This is incredible. That tracking dietary vitamin A correlated with vitamin A stores in the body liver, but it didn't correlate with retinol levels. So why are we running retinol? Why are we relying on a lab to tell us if somebody is vitamin A sufficient or not, when there are papers like this one suggesting that there's another way that perhaps is more accurate, and saves them money. So the interactions between micronutrients I've always found fascinating, and I will tell you, years ago, probably good 15 years ago, when I really dove deep into this, I came out saying, what do we think we know by giving certain things in isolation? Because there's so many interactions, and I don't even think we know the half of them. But here's some pretty interesting ones. So you probably know about this, but there's a very strong vitamin A and zinc interaction. You can see over here in this image, there's a few zinc-dependent enzymes that are required for, in this case, in the digestive tract, to turn beta carotene into retinal within the enterocytes, within the eyes, retinol into retinal. And then down here, you need zinc in order to make this thing I mentioned before, retinol binding protein. So if you lack zinc, you lack retinol binding protein, and I'll slow down here. If you lack retinol binding protein, because that's what transport retinol in the blood, you can have low serum retinol levels, although you actually have normal retinol inside the liver. Because you can't transport it, it kind of just gets stuck there. So the bullet points say that synthesis of retinol binding protein, zinc deficiency is associated with vitamin A deficiency. That's because you can't transport it. Studies supplementing with both of them improved vitamin A status better than giving vitamin A alone, partly because you can't transport it and it can't be converted properly in the digestive tract. Same thing here. Decreases retinol binding protein synthesis and thus retinol transport to the peripheral tissues. You get decreased activity of retinol palmitate, which is the retinol in the liver, required to convert retinol to retinols. So if somebody looks like they're low in vitamin A, maybe it's actually zinc. There's this iodine one that I don't think a lot of people talk about this one, but check this out. This is really fascinating. Really fascinating. And again, you know, anytime you put together a presentation like this, you really don't know what people are going to think. Are they going to like it? Are they going to not like it? They like the whole thing. But sometimes there's little nuggets within them that my hope is that you watch this and you're like, whoa, that, like, this was cool, but that was really, really helpful or super useful. And I think this is one of them. So check this out. In the thyroid, retinoids interfere with iodine metabolism, and vitamin A deficiency can aggravate thyroid dysfunction caused by iodine deficient diet. So there's a strong interaction there. However, the same paper went on to say combined iodine and vitamin A deficient diets have more significant impacts on thyroid metabolism than isolated deficiencies of one or the other. Vitamin A deficiency turns out it increases TSH, thyroid volume, and T4, and that's because if you lack vitamin A, iodine doesn't work as well in the thyroid. Vitamin A seems to improve iodine efficiency in the thyroid, and if that wasn't enough, check out this paper. Again, this is awesome. So vitamin A supplementation on thyroid function in premenopausal women. Check this out. So up here you have the vitamin. There's two groups essentially: obese women and non-obese. And then the obese women, so this was the obese vitamin A group, this was the obese placebo group, and this was the non-obese but took vitamin A. Now check this out, because TSH went down in the vitamin A supplemented groups, both obese and non-obese. T3 went up statistically significantly, and T4 went down a little bit, but you might think, well, that's not good. But in fact, maybe it is, because if TSH goes down, T4 will probably go down. And I don't think this really increased conversion necessarily, although it does certainly seem like it did. So just giving vitamin A in obese women or non-obese women improved their thyroid, okay? You don't see that in many thyroid presentations. So the last one is with iron. This is a big one, and I'll kind of cover this in a little bit. But check this out. Here's another one, just huge. After supplementation, this was in anemic women in the first place. The proportion of women who became non-anemic. So you get this? Anemic women were given the following and became non-anemic. 35% given vitamin A alone were no longer anemic. That's a lot, by the way. 68% of women in a different group given iron were no longer anemic, but check this out. 97% of given vitamin A and iron were no longer anemic. I'll say all that again. Anemic women, some given vitamin A, were no longer anemic. That by itself should be significant. Those that were given iron, kind of not surprisingly, were no longer anemic. But look at how many of them were no longer anemic when given both. These things work so much better together. Here's another paper. Low vitamin A is associated with low iron binding capacity and percent transferrin saturation. In some of these interactions, the mechanisms aren't entirely known. Influences iron absorption in the gut, although there's some disagreement as to how much or if it does always. And then vitamin A deficiency may trap iron in the liver so that it can't be used, similar to what I said about zinc deficiency and not being able to transport vitamin A. They went on to say, although vitamin A deficiency is a cause of anemia, why aren't we talking about that more? Further work is needed to characterize both the pathogenesis and public health importance of what they're calling vitamin A deficiency anemia. Okay, so the vitamin A anemia connection. So we just looked at the interactions. I still have, towards the end here, I don't know how I'm doing on time. Doing all right? Oh, gosh, doing great. If none of this made any sense or was that compelling, I'll show you the take home in a few papers in just a second. Now, this vitamin A anemia, I have a paper towards the end that says has been known for decades. What they didn't go on to say is in third world countries, because that's where most of the vitamin A deficiency is really well known. But as I've been pointing out here, just to summarize really quickly, number one is, are we consuming enough vitamin A in the first place? And I think that that's questionable, depending on somebody's diet. I think number two, we can't rely solely upon beta carotene being converted into vitamin A, retinol, because of a whole bunch of factors, diet, and as you saw, that whole list of different things, in addition to pre-existing conditions like, type 1 diabetes or hypothyroidism or who knows what, different chronic conditions. Can we assess vitamin A? I humbly don't think that we can as well as we think we can using laboratory methods. And if it were me, based on that one Chinese study done on children, I think that just looking to see what somebody's eating for a good 2 or 3 weeks will give us a pretty good idea. Remember, that didn't correspond with serum retinol levels, which is very significant. There's a number of different interactions between that we saw vitamin A and iron, vitamin A and zinc, vitamin A and iodine. And now we're going to look at vitamin A and as it pertains to anemia. Now, listen, this is fascinating. And I hate to actually admit this. This information, this material took me far longer than I ever would have expected it to do. I can usually kind of get through stuff fairly quickly. This was kind of a beast, I'm not going to lie. And the reason why is there's a lot of observations when it comes to vitamin A and these mechanisms that I'll show you, but it's just not an area that's really, really has been deeply studied. I think that it's just not interesting enough to researchers. For example, you might see vitamin A as it pertains to tuberculosis, all right, or malaria or HIV, but that doesn't really correlate to, or pediatrics in, third world countries, but that doesn't necessarily correlate to everyday practice and a nutritional practice in, industrialized country. So these mechanisms, I will tell you, are postulated, but they're not fully, they're not concrete. But once again, the papers I'll show you at the end will show you irrefutably that there's a strong vitamin A connection. All right, so real quickly, the proposed mechanisms as to how vitamin A impacts anemia is through iron metabolism in some way, which makes sense, through the production of red blood cells and erythropoiesis, and or from the modulation of the immune function. Now, again, I'll tell you that I look deeply into these things and very interesting, but not really concrete theories. However, there's no doubt that vitamin A will improve, as I'll show you, anemia. Okay, so we're going to take these one at a time really quickly. So the modulation of iron metabolism. Now, notice I say may because these aren't concrete. As I said before, vitamin A deficiency may trap iron in the liver and spleen so that it's not usable. So if it's not usable, then you can't use iron to transport it to the red blood, to the bone marrow in order to be able to make heme, to be able to fill it up with, fill up red blood cells. And so you might have a microcytic anemia because it looks like iron deficiency, but in fact it's due to vitamin A because it's being trapped somewhere else. It might impair bone marrow iron uptake. It may decrease the iron binding capacity to transport it, and it does influence ferritin levels. Now, this is going to be really interesting, and I'll show you this in a second. Sometimes it will lower ferritin, and for those of you that already know about this, you'll say, wait a minute, you're not supposed to lower ferritin if you're trying to increase somebody's iron in order to be able to make hemoglobin for red blood cells. However, if ferritin looks normal because there's inflammation going on, and as you'll see in a second, if vitamin A influences the immune system and ferritin comes down because it's no longer as inflamed necessarily, then perhaps ferritin goes down. It's very interesting. I'll show you that in a second. Also, it might influence iron absorption in the gut, although, as I said earlier, these specifics are not clear. Now, when it comes to erythropoiesis, here's the deal. It does seem to influence it, but man, researchers cannot nail down exactly how. And I looked a lot, and I couldn't really find much. However, what they say is that retinoids appear to regulate apoptosis in the erythropoietic progenitor cells, which these are essentially stem cells that can end up converting down into red blood cells and then regenerate themselves. But studies are conflicting as some studies show influence of vitamin A on erythropoietin in the kidneys, while other studies have shown none. So it does seem that it does impact erythropoiesis, but the researchers, again, can't kind of nail this down. The last one is very interesting because vitamin A deficiency does increase one risk for infection. Now follow this. If this is a big one. If during infection, iron is sequestered, which it should be, I've mentioned this many times. There's a paper that I read a long time ago that said iron is like chocolate to bacteria. They love iron because it helps them replicate and proliferate and infect a host. And bacteria aren't the only ones. Viruses can use it as well. But during an infection, the body sequesters iron. It hides it so that it tries to protect you from the bacteria to proliferate, and basically trying to, stop you from becoming septic. Um, During infection, iron sequestration and mobilization is decreased, similar to vitamin A deficiency. That's what it's saying. It gets trapped, and so it can't be utilized, leading to anemia of infection or anemia of chronic disease. Therefore, might vitamin A sufficiency, ready, improve the immune system such that iron mobilization improves. To put another way, let's say somebody has an infection. And going back to that early slide where I talked about the body's doing something that's protective on purpose, you can see an iron deficiency anemia in somebody with an infection, and it's done on purpose. And shame on us for giving iron to those people, because we're actually feeding the bacteria when the body was trying to sequester it in the first place. There's another example of the body protecting itself and us getting in the way. What this is saying is when you get an infection, actually vitamin A does go down during an infection. If you give vitamin A, maybe it supports the immune system, so that you increase the fight against the infection such that the body doesn't need to sequester an iron anymore, and it liberates it for mobilization, and then you can help with the microcytic anemia. Okay, so here's the crux of this whole thing. While the mechanisms may not be fully established of those three things that I showed you, those are probably the big three proposed mechanisms as to the vitamin A anemia connection, which is, again, it's a very well established one, which I'm about to show you. The connection between the two is clear. So let's take a look at some of these, okay? So this was looking at a whole bunch of different studies, and notice that all these kids, mostly, not always, because you had some other people, were given vitamin A, and look, increase in hemoglobin, increase in hemoglobin, increase in hemoglobin, increase in hemoglobin. If you look at, so let's go back. There is no doubt that vitamin A improves anemia, period, end of story. I'll show you that not only does it increase hemoglobin, but I said at the beginning, it seems to supercharge some of the other interventions for anemia, okay? So number one, vitamin A increases hemoglobin. Here's another paper showing that this was anemic kids looking at vitamin A or iron or both. And you take a look at this. So just look at this. This is fascinating. Vitamin A by itself increased hemoglobin a lot, almost as well as iron did, although iron was slightly more efficient. But if you gave them both, it increased even more. So for those of you that are practitioners, you should be asking yourself, oh my God, how many, and listen, this is normal to do. It's humbling, but I in fact, I enjoy this. You think, oh my gosh, like how many of my patients did I fail by not knowing this piece of information, that I gave them iron because their ferritin was low, their TIBC was high, they looked like they had an iron deficiency. Anemia, hemoglobin was low, MCV was low, and I gave them iron, and it improved. But maybe it didn't improve all the way. And I remember I had patients where it didn't improve as much as I was thinking that it would have. Well, maybe it was vitamin A. Okay, and now this is just for kind of eye candy. But down here, what they did was they looked at the difference in vitamin A versus the placebo. Iron versus placebo was better. Vitamin A and iron versus the placebo was the best of all. And it's kind of looked at each other. So continuing at the same thing. So check this out. So this was group 1, group 2, group 3. Group 1 was given 5,000 IUs a day of vitamin A. Group 3, because these were kids, was 3 milligrams per kilogram of weight per day of iron, because kids might weigh different. And then group 3 was both. Vitamin A alone, you guys look, vitamin A by itself increases hemoglobin. Why is my question? This not taught more in just the basic nutritional courses that we take when we're getting our degree. Maybe you had a professor that taught you this. I know that many people that haven't. Vitamin A increases hemoglobin by itself. Iron does it as well. And why didn't I include both in this one? Because there was no improvement in the group over iron, the group that took vitamin A and iron. Now we've seen it change in a couple of cases, and this one, for whatever reason, it didn't. Here's another one. How about vitamin A and zinc? I told you it supercharges. So these were given 70 milligrams of zinc or 3,030 retinol equivalents of vitamin A, or both once a week for 6 weeks. I'm sorry, once per week for 6 months. And check this out. So here you have again hemoglobin. So zinc improved hemoglobin. Vitamin A improved hemoglobin better than zinc, and for whatever reason, giving both didn't seem to have as much of an improvement. So once again, vitamin A improves hemoglobin, in this case, better than zinc. In the previous studies, not as good as iron. Here's another one, vitamin A and zinc. So this is an interesting one. This is 1,500 IUs of vitamin A alone, and then with either 10 or 20 milligrams of zinc. And so here, group A was vitamin A, group B was zinc, group C was both, and group D was neither. That was the placebo. And then when you look at the hemoglobin levels after just a mere 14 days, vitamin A and zinc improved hemoglobin the same amount, let's just say, but the one that took both increased it better. Now the previous study didn't show that, but this one particularly did. And this is what I'm saying, that it can supercharge your interventions for anemia. This was a funny paper because they gave the vitamin A in biscuits to the children. Why not? I think that that's great. But preschoolers for 9 months. Now there was different groups. One group had 500 IUs of daily vitamin A daily in the biscuits. I guess it was 500 IU biscuits. They had a 7 gram per liter hemoglobin increase. Some kids got 2,000 IUs daily in their biscuits. There was not an additional improvement over the 500 IUs, interestingly. One got 20,000 a week in their biscuit with no additional effect. But check this out. And this is these kind of things, you think you kind of have a handle on it, but then you see this and you're like, I'm not so sure. Some kids were given 200,000 IUs at once, maybe in a biscuit. That's a lot of IUs in a biscuit. And they had an additional improvement over the other ones in having a massive dose like that. Now, I would honestly say I'm kind of a slow boat person, and I would give a smaller amount for a longer duration, but that's kind of interesting to consider. I'm not really going to comment on it, but I found that finding kind of interesting. Same deal here. So here's a single 200,000 IU dose of vitamin A with repeat testing after 3 months. That was it. And check this out. Hemoglobin went up, but what I wanted, so this is positive or negative, right? So if it's positive, a positive 0.51, so hemoglobin went up. Now look at this. Ferritin went down, iron went up a little bit, and TIBC went down, and the percent saturation went up. This was a single 200,000 IU dose of vitamin A, testing 3 months later. Not only did hemoglobin go up, but this is what I want to point out to you. This is actually really important because you might see this ferritin go down and say, well, how did their iron improve? Serum iron is buns. It's a almost worthless marker, not entirely. Ferritin gets all the press for being the marker of iron storage, right? But I'll go ahead and tell you, of everything that I've looked at, for a variety of reasons, TIBC is like the unsung hero of the iron status. And that's because it's kind of a surrogate marker for transferrin, and transferrin, of course, is a protein, iron-binding protein made in the liver for transport of iron around the body. When TIBC goes up, it's the body saying, I'm looking for more iron. I'm sending out more taxi cabs to look for iron in the recesses of the body, to pick, like more Uber drivers to pick up and drive it to the bone marrow to make more heme. Okay, so ferritin is a good marker. Iron is not. TIBC, and what I want to show you is TIBC went down a lot. And that's an indication that the body's not looking for more iron. It doesn't feel the need to look for it. So ferritin went down a little bit. Maybe that's that immunomodulation bit. Maybe it was a little bit higher because there's inflammation. We're not really sure. But the fact that TIBC went down so much is an indication that the body was actually utilizing iron better, and therefore it wasn't looking for it more. And where did it go? Probably to help make more hemoglobin. Okay, anyhow. So this is my note at the bottom. Does this reflect a decrease in infection, an increase in biomobilization, or both? So here was a meta-analysis. This kind of summarized it for me. The meta-analysis of the clinical trials showed that vitamin A supplementation reduces the risk of anemia by 26% and raises hemoglobin levels. No iron needed. Compared to non-treated group, they talk about uh, teenagers and children. But what they say down here is a significant increase in serum ferritin was observed in trials conducted with pregnant and lactating women. Okay. They go on to say, therefore, vitamin A supplementation alone may reduce the risk of anemia by improving hemoglobin and ferritin levels. And I'll just say it again. I know some people are probably talking about this somewhere in the industry, but clearly not enough because when I present this, then people are wondering why they didn't hear it before. Now, I mentioned that there was a paper that kind of summarized everything that I said. So look at this. The relationship between vitamin A deficiency and anemia has been known for many decades now. This was done almost 10 years ago in 2014. So far, various pathophysiological mechanisms have been postulated, though they're not entirely sure about each one. Vitamin A appears to enhance hematopoiesis and mobilization of iron stores, possibly by increasing erythropoietin. Vitamin A could also prevent anemia associated with infection by its immune modulatory effect, and vitamin A deficiency might also alter iron absorption and storage of iron. So, how to use this information? How are we doing on time? Pretty good. So, what to do? Number one, I said this before, a CBC is one of the most inexpensive parts of a blood chemistry with a differential. If you, number one, have optimal reference ranges to go by, and number two, look critically at it. Don't rely on, in my opinion, what some people teach in the industry as patterns of this. If hemoglobin is suboptimally low, that's all you need. Red blood cells, and listen, I didn't even intend on talking about this, but listen, here, you guys mind? I'll just do this. Red blood cell, hemoglobin, and hematocrit, okay? So there are things that can pull this down, right? So these can all be low due to production issues, micronutrient deficiencies, as we saw. But guess what? Each one of these three things can be pulled up in dehydration or high testosterone. So let me ask you this. Can you have a woman who's dehydrated with PCOS that will pull these up, who is also anemic, which will pull these down? What will those show up as on a blood chemistry? You guys, those will be normal because you have influences pulling it up, like dehydration and high testosterone, and you have things pulling them down, like dehydration. So that's why you want to look really closely at hemoglobin. Look at those reference ranges that I gave you because that's evidence-based. This is not made up. Is when you start to see that hemoglobin a little bit low, in my humble opinion, you're done because you don't know, and I mean, unless you're looking around at the rest of the lab, are they dehydrated or not? Look at albumin, look at specific gravity in the urine. Do they have high testosterone? Look at things like T3 uptake. So this is number one. Look at a CBC. It's inexpensive. If you know what you're doing, you can catch all sorts of stuff that most practitioners will miss. Two, if they have low hemoglobin and a low MCV, you want to consider the standard things like iron, copper, zinc, B6, and vitamin A either by itself. You saw it raise hemoglobin in a number of papers. You guys, vitamin A raises hemoglobin if somebody's deficient, period. And it seems to supercharge other things that we saw like zinc and iron. Number two, because I personally think that, according to that one paper, looking at diet history is good enough. And leaves less to be interpreted than a lab with multiple different factors that go along with it. Evaluate diet history, look at other laboratory markers to rule in or rule out these particular micronutrients. Yeah, I'll leave it at that. Well, no. So for example, zinc, if you see low alkaline phosphatase, that could be a zinc deficiency. If you see low AST or ALT especially, that could be low B6. Anyhow, consider supplementing with preformed vitamin A, not just beta carotene. Take a really good look at the multivitamin because unless it says, retinol palmitate or something, it's probably just beta carotene. And then you're relying on the body to convert beta carotene to vitamin A, which in some people might be okay, and other people it might not. There's a whole bunch of factors that are involved with that. Give preformed vitamin A for 1 to 3 months if intake appears low. And then some questions that I think we should all be asking about this is, do you have any patients that are subclinically low in vitamin A? What do you think right now? Do you think that you might have a few? How would you evaluate that? How could you figure that out? Can we fully rely on the bioconversion of beta carotene to retinol? How can we best assess vitamin A status if laboratory testing is of questionable utility? And why, when giving vitamin A, do the other micronutrients seem to be working better? What are we missing? Why, when giving vitamin A, do iron markers and hemoglobin improve without even giving iron in the first place? And most importantly, can we afford to miss out on possible therapeutic benefits of a simple micronutrient instead of reaching for the latest, greatest, fanciest fad supplement? And I'm just going to spend 2 seconds on this. I don't need to mention any supplements. You guys know the ones that are popular. You guys know the probiotics that are super popular. You guys know the herbs that are popular, the fancy synthetic. But here, have we been missing out on something right in front of us? Like people say, hiding in plain sight. Vitamin A deficiency. Government says that people are good based on a lab assessment that's questionable in its utility. Um, why are we going for these super fancy, expensive things when right in front of us might be something that's very simple? So, quick summary, a couple pages of this, and then I think we have plenty of time for questions. The majority of Americans are not consuming the EAR for vitamin A when you look at the studies. Current biomarkers do not appear to accurately reflect vitamin A status. They're questionable at the very least. Bioconversion from carotenoids is questionable and appears to be overestimated, although they even said that this data may change. Even though the discovery of vitamin A was over 100 years ago, there are many unknowns about adequacy amongst many populations. There are a number of known connections between vitamin A deficiency and anemia. There are many proposed mechanisms as to why, and observations that other nutritional anemias like zinc and iron improve when vitamin A is also given. Vitamin A supplementation alone seems to improve iron status and reduce anemia risk, which, by the way, that's all you need right there. I mean, that should be compelling enough. And finally, in any person with anemia, vitamin A intake should be evaluated. And when I say anemia, I mean low hemoglobin, low MCV. Vitamin A intake should be evaluated, and supplemented vitamin A should be strongly considered.
And then we'll just open that up to questions. So wonderful presentation as always. There are quite a few questions. I think some of these from the beginning have been answered as you're going through. So I'll just kind of start at more towards the bottom of this. Here's a question for Dr. Walsh. Could the opposite be true where chronic infection depletes vitamin A?
Yes. Yeah, no, that's well characterized. And so that's really interesting. It's a big question that I have. Well, no, I can't say that. It's a question that I feel pretty comfortable with. The short answer is yes. Vitamin A does go down during infections. That is super clear in the evidence. The question in my mind becomes, is that protective and on purpose by the body, and should we intervene? Or is it evidence that the body's utilizing it and we need to be giving more? And I've said it before, I always question, like, should we be messing around with something? Is the body doing this on purpose? Because the more I've looked into that, the more cases of that there are. Now, I will say, however, so having looked at that, chronic infection does deplete vitamin A, even acute, by the way. Acute infection, vitamin A reserves will go down pretty quickly. It does seem to me that supplementing with vitamin A during infections is not sabotaging the body's desires and actually can help. But good question.
Great. All right. Could mycotoxins or mold have something similar to that have a depletion impact on vitamin A levels? Or somebody with vitamin A deficiency, would that increase the susceptibility to mycotoxin-induced symptoms?
Oh, that's a good question. The second part's really good. That's something I contemplate. The first one, I will just listen. I'll say something if I don't know it. I haven't looked at that in the literature, if mycotoxins induce vitamin A deficiency. I will say that it seems that viral infections might do that more than bacterial, though they both do. So then the question becomes, is anything that's impacting that arm, let's just say, of the immune system, kind of, I don't like the whole Th1, Th2 thing very much, but it works a little bit. So like natural killer cells. So the question is anything then that influences that part of the immune system, does that impact vitamin A? So do mycotoxins influence, natural killer cell activity and neutrophils and macrophages and some of those things? So the short answer is I don't really know. I haven't looked at it. I haven't seen it in the literature. It's possible would be my answer to that. And then the second question is actually a really good one. And I'm not going to go into too much detail on this, but I have huge questions in my mind why 50 years ago, nobody needed a low histamine diet or a low oxalate diet or a FODMAP diet or a gluten-free diet. And so all of a sudden, it seems like we are hypersensitive. Like oxalates are in food, it's normal. And you'd even argue that they're hormetic in a sense. So it's what makes vegetables good for us is these mild toxins stimulating us to be a little bit more resilient to toxins like oxalates. But why all of a sudden, and there's no doubt people will go on a low histamine diet and get remarkably better, but then that's not a sustainable diet for their life. Same with low oxalates. So the question is could vitamin A deficiency make somebody more susceptible to mycotoxins? And again, I don't know. It's a very interesting question. My question is, why are we more susceptible to all these things? I would even argue that our houses were probably moldier 100 years ago than they are now. I mean, if you think about like the early settlers in America, how come they were dying of dysentery, but not, sick building syndrome? But their old moldy houses were probably horrific. I would guess more so than we have today. We have air conditioning, we have heat, we have dehumidifiers. But why are we so darn sensitive to mold and oxalates and histamine? So that's a fantastic question. I don't know the answer to that. No, it is. It's a bigger, that's a thinking question. It's not like, what's the dose of vitamin A? It's, could vitamin A deficiency make us more susceptible to all these different things? And when you look at the role of vitamin A in the immune system, I think that you can make a strong argument for it, but I have no proof for that, if that makes sense.
Thanks. What's a safe daily supplement dose of vitamin A if anemia has been diagnosed?
So that's why I showed some of those studies because they gave different doses and they had sort of different effects. Um, I I'm not opposed to giving a huge bolus like that 200,000 I use a day um, is probably safe for most people, not everybody, definitely not pregnant. Bad idea. I would say so. For me, I'm pretty conservative when it comes to things, and I believe that we become deficient slowly, and therefore we should become sufficient slowly. I'm not in any big hurry for those things. I think 10,000 IUs a day is safe probably for about a good 3 months for most people. You could even argue maybe 20,000 IUs a day for 3 months. Beyond that, I don't think it's necessary, though those papers that use 200,000 IUs once, uh, and they had fairly remarkable results, that really gave me pause to wonder if maybe my slow boat methodology was the right way or not. But anyhow, I'd say minimum like 5,000 IUs a day. I think 10,000 if you think somebody's deficient with anemia for a good couple of months. But you should always be reevaluating and testing, I think, every 30 days, especially if it's cheap like a CBC or just a.
Thank you. Let's see. Dr. Sedano, and anything you would like to chime in or add or any feedback?
Yeah, sure. Doc, really a wonderful presentation. And just to kind of sum up on my end, I mean, my study of vitamin A, I kind of look at it this way, that it is needed for gene regulation. So, and
Yep.
it affects the vitamin D receptor, the thyroid hormone receptor, and a receptor that you may know about or may have seen it, the peroxisome proliferator activated receptor, or the PPAR receptors. Those are the ones directly involved in the immune system response. So vitamin A is needed for all of that, for vitamin D, for thyroid, and for immune system response. Very powerful vitamin when you look at it from that perspective, as it is involved in gene regulation and gene transcription. So that's kind of my short message here. Hopefully that's helpful.
No, it's fundamental. I mean, when you consider, it's nuclear activity, and to have, it's funny because if you have receptors on a cell membrane, it's important, you could argue. If you have receptors in the cytosol, that's important.
Yeah,
But if you have,
I'd like to mention that You know, when I went down my rabbit hole several years ago with vitamin A and looking at the inhibition that high levels of homocysteine can have on vitamin A, going from retinol to retinoic acid, and also the potential for environmental toxins, specifically heavy metal toxicity that can gum up the works there too. I found a lot of research on that too. So I just wanted to share that, you know, with everyone.
Yep.
All right, guys. We have a few other ones in here, but they're really related to specific supplements and dosages. And Dr. Walsh will absolutely address some of the rest of the questions with this. So why don't we just move on and we will wrap up for tonight. So if we can go to the next slide. Of course, just a reminder, ask the doctor, free email consultation with Dr. Sedano, any help with lab interpretation, questions on clinical conditions, comparison to different labs, all of that on the left-hand side of your portal with that, a free email. Otherwise, you can sign up for a live consultation. It's amazing what you do, Dr. Sedano. Thank you, and let's move to the next slide. And now that we've learned about vitamin A and anemia, these are just obviously some basic labs that can be ordered right from your Avexia account. And we'll just go to the next slide. And really, for any questions, issues, you may contact Avexia Diagnostics by email or at info@avexiadiagnostics.com by phone. We are here 5 days a week at extended hours, 8 a.m. to 8 p.m. Eastern Standard Time. Thank you so much, Dr. Walsh and Dr. Sedano, for this informative presentation and answer to the questions. A recording of this webinar will be available by email in the next few days to everybody that is registered. Thank you again for joining us for this webinar event. Until next time, from everyone at Avexia Diagnostics, stay healthy, stay safe, and we wish you all the best on your pathway to wellness. Good evening, everyone.